Good morning. So today I'm going to introduce SDCC, the C compiler for small devices like the 8051. But I wanted to first recap and wrap up the last Wednesday's material. So quick review. In the 8051 instruction set architecture, they do define their interrupt vector, which as you remember is the address of the interrupt service routine. So timer 0, timer 1, there are two interrupts. They are at address BH and 1BH. Int 0 and int 1 are the pins that can trigger interrupt from the outside, and their interrupt vectors are 3 hex and 13 hex. Now serial port is at 23 hex. So that is the starting address of the ISR for the UART. And now there's each interrupt has an associated flag, as you remember. For UART, there's TI and RI. So TI is set after completion of transmission. So that means the UART is ready to accept next byte. RI, if it's set to 1 by UART, then that means it has just received a byte that is ready for you to read, or you can think it's a data valid bit. And in the case of UART, it's the programmer's responsibility to manually clear that bit. So hardware sets it, programmer clears it, right? So that is a kind of a handshake protocol. So then the hardware can know, okay, well, you just read it, I can put the next one in. Okay, and then that next time around, if you check, if it's not ready, it's still 0, and the hardware sets it to 1. Okay, so that's done manually, but not all flags are cleared manually. So in the case of reset, int 0, TF0, TF1, these have automatically flag clear. What that means is only when you use these as interrupts, then by jumping to the ISR clears the flag. Okay, why is that? Well, because the transmit and receive share the same ISR. So if you don't clear one, you don't know which one you handle. In fact, your ISR calls, and then it's up to you whether you want to receive or transmit or both, right? So that's why you have to do it manually. And whereas the other ones, there's only one, did you handle or not? By jumping there, it's assumed it's handled, so those flags are cleared automatically. Anyway, so we'll get to see more of these, but that's just a concept you need to keep in mind. So with serial port, a quick review. So there is one special function register with a mnemonic of SBUF for serial buffer. It's the same name, but it's actually two separate registers. So when you write to SBUF, it transmits it out. When you receive, the received one is in SBUF, you read it out, right? So they are physically separate registers, but they're just named the same. Why? Because it's not ambiguous. When you move to or move from, that's pretty clear which one you're indicating. And just for convenience, they didn't make a separate name. In fact, they're the same address, but then the side effect is they go to different physical registers. Anyway, so the flags TI and RI, those are the ready flags, so to speak. And you can poll them, or you can set it up as interrupt. So user must check whether TI or RI is set by hardware, and user is responsible for clearing the flag. It's one ISR shared between TX and RX. And then, so this is, I think we took a quick look at this layout. So you remember ORG, that says where should the assembler generate code, or at least indicate where the code should go. So if you do org 0, that origin 0, then what it does is jump or ljump. Jump is essentially a pseudo instruction. It gets mapped usually to ljump to main. And here I'm just using a different main, but C has a lowercase main. Here I'm just using capital main. It really doesn't matter. That's just a symbol. And then it jumps out of that interrupt vector area so that you can define your ISR, right? Your ISR could be located right there if there's enough room. If not, you can certainly jump out of it to somewhere else there's enough room. Anyway, so we can do a jump to main from org0, and then for defining the ISR for the UART, then we do a jump. Oh, first we do org23 hex, right? That's the interrupt vector for the UR ISR. So then we do a jump to serial ISR. Why? Just because I don't want to commit to like fitting everything in there. I don't want to have to count. So it's much easier if I pay the cost of one instruction, jump out of it somewhere else where I don't have to worry about how much space it takes, right? So, so on reset, it goes to main, and on interrupt goes to a serial ISR. That's how to read this. So main, what does it do? Well, it calls the init UART subroutine, and then we can define that elsewhere. And then it set B to set the bit. So remember, when you do bit assignment to 1, that's set B. Instead of move to a bit and then #1. So ES and EA. ES is to enable serial ports, so UART, as an interrupt. And then EA is enable all. So if you read the 8051 documentation, enable all doesn't really mean actually enable all. It's kind of an AND bit with everything else. So you can individually enable, interrupt, or disable them, but none of them take effect unless they are ANDed with EA, right? So if EA is on, then that means the other enabled ones are actually enabled. But if EA is off or 0, what happens? Even if you try to enable those, no, you end it with a 0 still at 0, right? So why do you do that? Well, it's a way to totally turn off all interrupts and quickly. So by setting one bit, all interrupts are off, but you still remember which ones should be on. So next time you turn EA back to 1, all the ones that were individually enabled, they are actually enabled. All right? So quick way to turn off all interrupts and restore all enabled interrupts, right? Without affecting the individual ones. So EA is kind of this guard bit that allows all the individual ones to be ANDed with it, so you can disable all of them, but remember their individual status, or re-enable them quickly. And that's very useful later when we do atomic operations. Why? Because if you start doing threads, context switching, there are places where you simply don't want interrupts to come in. It's bad. So that EA bit is going to be revisited several times in our project. So just keep that in mind. Now, then to do a loop, what do you do? Well, you just do jump loop here. It's the same line, all right? Serial ISR, what does it do? I think we've seen this before. JMB, TI, check RI. So that actually is not polling. That's just a check. Jump if bit is not set, or jump not bit. That's JMB. So is TI set? If not, then I skip to check RI. So here the sequence is check TI first, and then if not, then check RI. And even after you check TI, well, first thing you do is clear it, and then you fall through, right? So that's like if, then if true, then you do the clear TI, then fall through to check RI. Then it does another one. Here we don't do any transmit, so that's why it just, even if somebody sets it to true, or hardware sets it to true, it doesn't matter. I just clear it anyway and go on. And check RI would be similarly, if RI is not set, well, we're done. Jump to serial done, and RETI, that's return from interrupt, remember? So unlike subroutines, you use RET. If ISR, you use RETI. Just like in MIPS, regularly there's RET for return from subroutine or return from interrupt, ERET, that's MIPS instruction. But anyway, so there's usually a separate instruction. Actually, there's always a separate return instruction just for interrupts. And you move on, and then what do? Re-serial port. So from SBUF, read it into accumulator A, clear RI, and then what do? Well, you can do the display right there if you want. Add A, and then just subtract the ASCII code out of it, and then call the subroutine. That theoretically, that's what you can do, but we'll show you in practice why that's not a good idea. Yeah, you had a question. Wherever it got interrupted. So here, there's only one place. The main program, remember, it gets stuck at the loop here, right? Loop here at the last line of right here. It's just jumping. It's not doing anything. But in a real program, it could be doing useful thing. So wherever it gets interrupted, that's where it returns to. You don't know in advance. You have no idea where it can be. But it's always between two instructions. Cannot be within an instruction. Okay? Now, so code for init UART, well, you don't have to know this detail. You could read the data sheet if you want, but just copy and paste, that's fine. No plagiarism here. Display, we've seen this, right? Move the A, remember we use A as the parameter, and then use A, add A plus dptr, right? And dptr is the base address of that array. And then do the move to P1. Yeah, okay, we've seen that. So now remember to do this, with UR you have to set it to 11.052 megahertz. 4800 baud, that should work, okay? And then if you actually try running it, you see that code initializes and just PC stays at that same address, 2C, at least on my assembler. And then UR will trigger interrupts and run. And you should get a chance to try this for yourself. Okay. There are other interrupts, and so over time we'll add these. Interrupt enable, so these are all E something, X0, X1, so external 0, external 1 source, corresponding to int 0 and int 1 pins. And then there's ET0 and ET1, T for timer. And later we'll be using timer. Right now one timer is used for the serial port because it needs to do the baud generation. Second one we'll be using both as kind of a time counter and for your context switching. Because even if nobody does a system call or anything, you still want to periodically do a context switch. So that's going to be triggered by timer 0 in this case. Now on power up or reset, you can think of it kind of as an interrupt, and its interrupt vector is 0. So that's why when we didn't enable any interrupt, it just starts running from 0. Same idea, okay? So that was a quick review of last week, and now I am going to go into SDCC for EdSim51. Well, SDCC is a free C compiler, more or less NCC style. So most of what you can do in C would work, and it does support a number of new keywords or these you might call somewhat like directives that you might not see in your regular C, but macros and all those work, okay? And also a few different data types, okay? So we'll see how this works. So you should have downloaded it by now, and it's cross-platform. You should be able to download for most of the general purpose platforms. And we use this as opposed to a commercial one. There are commercial ones like Kale or Kyle, however you pronounce it, and IAR is another very commercial one for embedded. They target different architectures, especially embedded ones. They're both very old. I mean, I should say companies are old, but they keep their product up to date for many different embedded processors. They're kind of expensive too, several $1,000s per seat. And they're both out of Europe, I think. But Kyle gets acquired by ARM, I believe. And of course, 8051 is one of the main ones they support. But we'll use SDCC. Their syntax is a little different, but I think you'll get used to it pretty quickly. So you should have installed it. And if you're on Windows, don't use the DOS version, use a Cygwin version. I think it's better. So it stands for Small Device C Compiler. SDCC. It's open source, retargetable. It actually generates code for different instructions architectures. Include 8051, which is the default, so you don't have to specify minus something. There's also Z80 you may or may not have heard of. AVR from Atmel. May not be familiar. If you play with Arduino, you probably have used some AVR. Tiny, that's another one. Maxim DS390, DS340. Motorola had an 8-bit one HC08 that was pretty popular. And certainly it has a PIC, that's from microchip. And PIC ones are weird because its instruction words are not multiples of bytes. It has 14-bit instruction words and 16-bit and some weird ones. But PIC is certainly one of the very popular ones for a long time. But nowadays, a lot of people move to ARM or the Cortex-M type of with a thumb instruction set, thumb 2, so mixed 16-bit 32 instructions. But 8051 still is used a lot. Why? Because there are free or very cheap cores that people can integrate into their system on chip. Okay, SDCC actually comes with several commands. If you install and put in the same path, then it actually gives you the SDCC. So I'm just gonna, all of them have SD for small device, right? CC, CPP, AS, LD, DB, AR, renlive, NM, OBJ copy. If you just read the red parts, those are present on your general purpose systems as well. You may have the GCC version, but certainly GCC was just a G in front of CC, and then a CPP. You probably have, that's a C preprocessor. AS for assembler. Now this one just happens to be AS8051. Well, SD AS51. Okay, LD, the link editor. And then there's a simulator, which probably doesn't have a corresponding one elsewhere, but that's bundled here. DB for source debugger, but we're not going to really use it because it's not exactly supported on EdSim. If you use UCSim, it's probably okay. Anyway, AR, renlive, so those are additional tools for making these libraries, but you probably won't need to use those. There's another one specifically for processing the hex file defined by Intel. So that's pack IHX. So that's a way to clean up the hex file. Essentially, you might call executable, but really it's human readable. And we'll see examples of those. What about data types? So it actually supports bool, which is Boolean. And in this case, it's not a byte or a word faking to be a bit. It's actually a bit. On 8051, in IRAM, there's a section of memory, actually 256, that are individually addressable. Okay, half of them in the general purpose data space, the other half in the SFR space. That's why in your GPIO, your P1, you can do P1.1, P1.2. Those, well, but those would not be called bool. They have a S-bit type. We'll talk about those. But it's compatible to bool. So you have at least an area where you can allocate a single bit, which you don't get on other general purpose processors. So I think that's pretty cool. You have char, by default it's signed, okay, and bool is unsigned. But you can declare unsigned char. So if it's char, it's minus 128 to 127. Short is 2 bytes. Int, 2 bytes, not 4 bytes, not 8 bytes. Okay, here int is 2 bytes. Now, if you want 4 bytes, you could do long, but it's not natively supported. So anything that's more than a byte, not natively supported. Okay, what does that mean? That means it's not a single instruction that can handle 16 bits or 32 bits. What does it have to do? Call a subroutine, call a library function, whatever, right? So it has to emulate those longer operations in software. And what does that mean? You can still do it if you run. If you don't care about code size, you don't care about speed, fine, by all means do it. But most of the time, you probably want to stick to byte as much as possible. Even for certain pointers, you want to stick to bytes. Unless it's like a code memory, then that's 2 bytes, then that's native. Anyway, even floats get supported, floating point, but 8051 doesn't have floating point, so what does it have to do? It has to use software to emulate those floating points. So it's probably 100 to 200 instructions just to do a simple floating point operation, as opposed to a single instruction on one side with hardware support. So avoid floating point whenever possible. Pointer depends on what bank, and so we'll show you. Now, you can't do a pointer to a Boolean, and you can't pass or return a struct or a union, but you could do assignment. That's supported by the latest version of SDCC. You can't do variable length array. I don't know. I mean, you can do pointer for sure. You can't do long, double, but we don't even be needing any of those. Now, flags. So very similar to your general purpose CC or GCC. You should have tried this. I mean, if you don't believe me, try it on your GCC. Same flag. Minus big S. What does it do? Compiles a .c to assembly. Now, the assembly could have a different suffix on different architectures. Some of them have .s for assembly. Why? I don't know. But in SDCC, assembly is .asm. So same stem. So file.c gets compiled to file.asm assembly. But they have slightly different syntax than the Intel-defined syntax used by EdSim. We'll show you some examples. So if you just want to see the assembly output, do the -big S of that C file, okay? Then read it. Now, it has a lot of other junk in there. We'll take a look. But that's one way to examine the output. In fact, it may be a good idea for you to make sure, is SDCC doing what I think it should? Sometimes it does. Well, most of the time it does, but a few times you may be surprised. Or it says, hey, that's kind of stupid. Why would you generate code like that? You can craft so much better assembly code by hand. In those cases, you say, okay, no, this part I'll just write by hand. Other parts I'll let SDCC do, okay? Anyway, so you get to have some fun with this. And there is another one. So if you do like -c, you probably have learned this from your C programming class, right? Say yes, yes. So -c allows you to compile separately, and then separate one links them, right? And then on a general purpose, if you do a -c file.c, you get what? File.o, right? And then you can do a separate cc to link all the .o's together into an executable. Here, you don't get .o, you get .rel, but similar idea. What does rel mean? That means it's relocatable object. .o means object. Well, really, it's the same. They just didn't want you to get confused with your general purpose and your cross-compile code, right? So you don't accidentally link 8051 code from SDCC with the rest of your GCC. So they named these separately for that reason. So .rel, in fact, you can even take a look if you want to, but it's probably got a lot of stuff you don't understand. But that's okay. It's relocatable. That means it's pre-linking. Why? Because you compile separately, and then the addresses haven't been resolved until you put together all of them together, right? It's because then you know, okay, this is how much space, and the label it gets offset by this much, offset by those. Then after you determine the locations, then you fill them back in. That's what the link editor does. Okay, so this is really good for a separate compilation, and very soon you'll have to do a separate compilation. Otherwise, your code is not going to be manageable. All the SDCC, just like CC, can have a -o for the output name, and then you can do -o something. Okay, if you don't do -o, one of the flags, one of the options, just like GCC and others, it does the default, and like GCC or in regular CC, it does the a.out. If you have a file name, it does file name dot, just whatever. But in this case, you do want to give it some file name. So you can do if you don't give it the name, the default name is .ihx or Intel hex. But normally, if you want to do cleanup, you convert from ihx to hex. But you could just do directly to -o the .hex file. And then that is what you load into EdSim. Okay, EdSim wants a hex. And if you do ihx, it says, oh, I can't find it. Well, then you enable like the show all file suffixes, and then it'll show the ihx. Okay, so now suppose you have a program named delay.c, and that's reused over several different executables. What can you do? Well, you just compile once. SDCC -c delay.c, that makes delay.rel. Okay, and then you don't have to recompile it anymore. And as you can see, I'm leading to makefile. Yes, I'll give you makefile. You don't have to actually be able to write makefile. I give you makefile, but eventually you should know how to write makefiles. And that's very convenient because then if something changed, then makefile will compile those. If not changed, then just leave them alone. Save you compile time and link time. Okay, so then if you want foo.c to be linked with delay.rel, what do? Compile foo.c separately with the -c, then you have the .rels, right? So SDCC -o, the output name, so -o foo.hex, then the .rels together, right? So that's the syntax from the command line. So once you have the .hex, you can load into the simulator, EdSim, to run. Okay, so let's do the very first hello world, well, not hello world, right? The example. Remember that was the move of to P1 with # hex 24 on SDCC. That's what it looks like. First, # include 8051.h. If you install properly, it'll find .h. And then void main void. I mean, you say, hey, main is supposed to return an int, right? Well, it doesn't really care in this case. So that's okay, just do void. And what about argc, argv? Well, no, we don't do those. It's just a label, okay? And then P1 gets hex 24 in C syntax. Now, you understand this, right? Very easy to understand. And that corresponds to that org0 and then move P1 comma pound sign 24H, right? And so how can you do this? Well, if you do this, if you just say, hey, I just do SDCC main.c, that's how I did my hello world, right? GCC main.c and then gives me a.out. And this one gives me main.ihx. Will that work? Not likely. So what we can do is to see, okay, I'll just do a demo. And you should try these things too. Test0.c. Okay. Oh, there's some stuff. Just ignore. Pretend they don't exist. And so that's this program. Okay. And then SDCC. What is it called? Test0.c. Say main undefined. Oh, what do we do? Oh, yeah. Okay. Then we do main. How about that? Yeah. Okay. So test.0.ihx. It exists. And what do you think it looks like? Test0.ihx. Ooh, that's not very understandable. How about let's look at ASM? Okay, it's like, huh? What? But it says at least it's created by SDCC, all right? And then there's all these .global, but as you can imagine, that's the compiler, the assembler directives, right? So they don't correspond to anything real. Now there's P0, SP, DPL, DPH equals to, oh, these are the addresses for those special function registers. But still, no, these are not instructions. There's a start, stack, okay? There's all these other things. That gets kind of complicated, but no instruction yet. We haven't seen my move. Oh, I do see a jump, ljump main. Okay, do you see that? So that, remember, is from the startup, right? So that's like the reset interrupt jumping to main. We showed that assembly example earlier, right? And then it just doesn't do anything after that. Now, oh, it does show our main right here as a comment. And then main, what does it do? Well, these are not assignment statements. These are more like, remember the EQU, the assembler directive, right? Think of it as a macro, right? And then P1, P1, okay, here, that's line 3 of the C program. P1 gets hex 24, turns into a move of underscore P1 and then pound sign hex 24. So at least that's readable. You understand that, even though it adds extra stuff like underscore in front of P1 and then pound sign. It doesn't do 24H like the Intel syntax is the C syntax 0x24. So there are some differences in the syntax, but that's okay. At least it's understandable. Okay, but that does mean that if you have to inline any assembly for SDCC, then you need to do it in this syntax. It's a minor adjustment, but not too difficult. Then main ends, and then there's RET. You see that? That's returned from the main. All right. So there's that. Okay. So will this work? All right. So let's do pack IHX, test 0.ihx, test 0.hex. That cleans it up. It says okay. All right. And let's see. Still. It's like, wow, that's a lot of junk in there. I mean, I was expecting just like 3 bytes for my little move instruction, right? What's all this junk? Well, it turns out if you're just doing an SDCC, just like GCC, that it actually does a compile and link, which means some magic is happening behind your back. It links in some stuff that you don't expect. So what does that look like? Okay, so let's do a reset. I was running some other reset. Okay, now load. Where do I do load? Okay, how do I reset? Huh? I reset. Where's my, load, sorry. Test 0 here. So that just loaded. So we do see a jump here and then to 0 hex. So 0, 6, that is this move. Okay, so that's move 81H and then 07. Okay, so that means it's doing a jump to something I didn't actually expect. Now what about 62 hex? So if we go down to 62 hex, move of 90H #24H. Does that look familiar? Yes, that's our move to P1, right? So our main actually starts at 62. So what happens to all this code between the 0 and our code? So that must have come from library because I didn't write that code. Somebody else wrote that code. Okay, so it turns out SDCC does some magic behind your back, and we probably don't want that because okay, let's just try to run it. Does it do anything? Okay, it's running well, kind of slow. Let's do update 100 times. Not really showing my 2 letter. So that means it went off to some magic space and never came back. So so that means that you can't just do a single pass type of compile. Okay, so you have to do something different. But at least we saw the L call to main and then this or something like that. Okay, so it just happens that there's some other junk that happens in between before we get to our main. And this is what the hex file looks like. So now, if you're interested, this is how it looks. So they are divided into fields. The first 2 hex digits is essentially the record type and then the address, and then followed by, the count, address, type, data, and then checksum. And why this? And it was because in the old days, when you program these, you have to do it over a text terminal to a programmer. And so that was done over the text terminal. You copy and paste. And that's why it was done in this human-readable hex format. But you can lose characters because of race condition or anything. So that's why there's checksum. But anyway, that's just for history reason. And then we see hex 62, right? Remember that was our main. 75902422. That corresponds to the move. Remember, move was 3 bytes, and then RET is 22 hex, and then there's a checksum 4F. So that's where main is actually located. Okay. Well, I'm not going to ask you to try to disassemble from hex back to your assembly code, but at least you should be able to recognize after seeing enough of this. Okay. Anyway, so all that magic code was startup code. And that's automatically linked in, which is not necessarily desirable for our purpose. We do want full control. So what we do is then we have 2 ways. One is to rename main as something else, recompile twice, and then it'll do the right thing. But that way you don't get the interrupt service routines. Second way is we figure out what those special linked in library functions are. Name them, override them, by providing empty functions for them, so that then they won't take those from the library, because then that makes your code self-contained. You have full control. So what are those magic functions do? Well, one is startup. So it's named SDCCGS in its startup. So that's from 0 jumping, or whoever. It actually after it does all the other initialization. But whatever it is, what we can do is just have it call our main, or wherever you want your name to be named. Now, this lowercase name, that's just a C programming convention. To assembler, main, uppercase, lowercase, whatever, doesn't mean anything. It's just another label. To C language, the main has a special purpose, right? It's kind of the entry point to your program. So we can support that by doing a jump from this startup function to main. You could do a call, or you could do a jump. It doesn't really matter, okay? But for convenience, you just waste one little instruction, but that's okay. Now, what about these? MCS51, that's gen RAM clear, X init, X RAM clear. You can kind of guess what they are, right? Remember 8051 has different banks. There's the internal RAM, there's external memory, and external RAM. And so these are initialization. So a lot of times what might happen is you might want to clear your memory before you run. That's not always the case, but SDCC at least let you have the hooks if needed, right? And so, because some C programs assume if you don't initialize any variable or array, it defaults to 0, remember? Well, somebody has to actually clear it. Otherwise, memory just retains whatever junk it does. We don't want those. Besides, we don't have any external memory anyway. So, well, we just define those functions and then define their body to be empty, 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 empty. So what they do then is turn into a return. Call, return, call, return, call, return. That's it. So on startup, goes through all those functions and then do nothing and then enters our main. Okay, so that's the way to do it. And now, so what do? We can do the same thing, but then we compile 2 separate times. So SDCC minus C to generate the REL, and then we can do something that's not main, because if you do lowercase main, then SDCC thinks that's the entry point and it links in all the other ones. If we name it other than main, it's going to complain, hey, there's no main, but it does it anyway. Or you can name it main and add those things back in. Okay, so I'll show you the 2 different ways to do it. All right, so let's go back here. We do this. So this is the first way, which is to name main. That's not the C style main, right? This is just, I mean, you can name anything you want. Just it's the first thing. So SDCC minus C test 0.c, and then SDCC, and then we can do minus O test 0.hex, and then test 0.rel. Oh, that didn't complain. Okay, so now let's see, more test 0.hex. What does that look like? Oh, much shorter, remember, compared to the previous one. Previous one has a lot of junk. Now it's 2 lines. And in fact, it's just, in fact, this other one is just at the end of the record, and then that's it. Checksum is FF. So it's really just 1 line. And so if you are good enough, you can probably recognize those 3 bytes. Remember the magic 3 bytes? 75 is move, 90 is P1, and 24 is the hex 24. Right? You should be very comfortable with hex by now, right? So there, that should do the right thing. In fact, let's just load that in. So let's reset it, load it, and then let's load in this new hex 0. Hey, that looks very familiar, right? We can assemble. That's move, and then okay, and then we can do run. There, that's our hello world. The 2 and then the dot. All right, so that's one way to do it, but that is just a kind of a cheating version. The better way is to put back the stuff that I talked about, and then you can call it main. In fact, you should call it main. So this is the second style. So basically, somewhere you define your, probably in the same file as your main, define void, 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 and with the SDC GS init startup, gen ram clear, gen x init, gen x ram clear, and then the startup calls main. Okay, let's see what this looks like. So it's a little bigger, but this is the more general way. Yeah, this one you should use the little main. Yeah. Okay, so let's do compile. So it's the same flag as before, and then there. Okay, now let's take a look at. Okay, so now this program is a little bigger, but it should do the same thing because it went through all those init ones. Okay, so let's reset, load, don't save, and then test 0. Okay, now you see there's more sjump to these other init routines, and they don't do anything other than the startup. Startup does a jump to 9, and 9 does that main, right? Remember right here, right? So that you can tell that's a GS init, and then calls or jumps to main, and then main right here. That does the move, right? So we can assemble there. So that's exactly it. All right. So that's you should be able to get to this point. right? Oh, here, if you do SDCC, then that generates .ihx, and then you can move it or use pack.ihx to make the .hex file. That's what I mean over here. Okay, so so let's try a few other things. So I gave you some examples. Now remember, we also have this 7-segment LED for different digits, right? So you can write these all in C and .c and .h. So what's the .c gonna look like? So here, what we have is okay, here the 8051.h include, right, and then LED 7-segment, we define a function, and whenever possible, use all char or unsigned char. That's okay. So LED 7-segment pass a parameter char num, and then you guys should know this, right? Static, and then double underscore code that says we want to use the code memory for our lookup table. So that's how you say it in SDCC. Right? And in the assembly, well, you're in code space anyway, so it's in by default it's code. But here, if you don't say it, it treats it as data, right? So you do have to say which memory space. So static just says don't make it like an auto local variable. This is local inside this function. Static just says it's one instance. Code and char LED data, and then this is just. It's not a variable size array, it's just static array, but the dimension is determined by the initialized data length, right? So this is that table we use for LED segment to turn on and off, right? And then so once you have the table, what you can do is do a return of LED data sub num. So basically that does the lookup, right? So the num gets looked up in there, and then what do? Then we can do a display. Display basically does P1 gets function called result of LED 7-segment of num, right? So basically whatever you pass to LED 7 to look it up, and then P1 gets it. Of course, you can merge this in with display LED if you want, but okay, I just wanted to illustrate a point here. And then you should have your .h file in C. Remember, you should use header files to provide type signature, right? And then usually you want to make sure your .h doesn't get included multiple times. So what do? The standard way is if not def, some tag, and then you define it, and then end if, right? So that way, if it's been included, that symbol has been defined, and then it'll skip the rest of it. Okay, so we can do the include 7seg LED or 7seg LED 7seg.h 20 times is only gonna use once, right? The other ones all skip. Anyway, so to use this, you include it. So here, your main can do void main void char I for I from 0 less than equal to 10. Oh no, less than 10 I plus plus, and call display LED sub I, right? So that way it'll call this function, right here, this then calls that other function. But then this allows you to compile them separately, linked together, so that the 7seg LED, or I should say LED 7seg, can be like a library reused over different programs. All right. So the way you do this is SDCC minus C test 0.c, so that's the main one, and then it's minus C. LED 7seg.c, and then that's your kind of the library, right? And then this pass the -o.hex to link all together the .rel files, right? And then your output should be this one. But the order matters. Here we're relying on main because we're not doing that other the GSInit other trick. So this code size is a little smaller, but main should be linked first, and then there's no interrupt allowed in this case. Okay, so we could try this out. I actually did try this. Okay, so we do this. SDCC minus C LED test 0.c, SDCC minus C LED 7seg.c, and SDCC minus O LED test 0.hex and then LED test 0.rel, and then LED7seg.rel. Okay, that did create a file, bd test 0.hex. Okay, so let's, that looks like a good hex file. So let's load that in. Reset, load, that's, what is LED test 0.hex, is that right? LED test 0. Yeah, that's right. Okay, open. Okay, now it basically disassembles it, and then assemble, and then run. Okay, so it went over quickly. So it now is stuck at 9. So it was actually pretty quick. Yeah. So let's update frequency. Let's do 1, and then reset, assemble, and then run. Okay, let's see. 0, 1, 2. Well, you can believe me, it works. I tried it many times. 3, 4, 5. You get the idea, right? So, so you can try to see PC. So it's 7, 8, and then 9, and then jumps into Neverland. So it's undefined behavior after that, because we don't know what happens after main. All right. Anyway, so you get the idea. All right. So that actually works. So try it out. Try to make sense of it. And if you want to use lowercase main, you just have to fill in those gs init functions. Right. Okay. So keywords, storage classes. So there's double underscore these. So these are SDCC only. They're not in your regular GCC. Right. So data for directly addressable. Another synonym is near. Okay, and then there is iData, that's indirectly addressable internal RAM. So that's mainly on the 8052. 8052 is kind of a weird architecture, but there's another hack where it's a direct address, but then same as your SFR address, which is 128 to 255. But those are indirectly addressable only. But we will only be using that, so don't worry about it. So there's bit. So bit, that refers to an area where you can actually address individually. But that's only in the data space. Now external RAM, so that's Xdata. We don't use external data, so don't worry about that. Or FAR, that's a synonym. PData, page data, no, we don't use that, so don't worry about it. We only use code. So lookup table should go there. The function should go there. SFR we do use. So yours, but then they're all defined in 8051.h. So if you can find 8051.h somewhere in your SDCC directory, you can take a look. It's all defined using SFR, or you could do sbit. That's so the bits in the SFR, they have their name. So we mentioned EA, right? Remember the enable all or enable serial ES. So enable timer 0, timer 1, right? Those are S bits. So we can do a serial echo. So compile this with UR echo.c, and then the REL gets linked into hex, and then that works with a serial port. Okay, and then yeah, so you should be able to try this, but if you want, I can do a really quick demo. SDCC minus C. UR echo.c. Okay, and if you get this implicit overflow constant conversion, don't worry about it. Oh, right here. It's right on the screen here. It's exactly the same thing. No, it's exactly shown on here. The same thing. I'm not cheating. It's exactly the same. Okay, so that's exactly what it is. So initialize and then do the while loop. Well, not RI, so this is polling, right? Do nothing. And then once RI is set, read from SBUF into C, and then C is actually chart, right? Remember here. And then RI cleared, SBUF gets C. So it reads it from RX, writes it to TX. That's what it's doing. And then while TI, well, not TI, then just wait. And then once TI is set, that means data got transmitted successfully, you clear it. Okay, so try this out yourself. I shouldn't have to show you. And of course, you know, type it in the the serial port window. So that's right here. Yeah. So you type in TX, then TX send, that goes into the RX, right? And then when and you send. So this is really kind of complementary to the 8051. Okay, and then do the polling. You could take a look at the assembly, compare, right? And so there's a poll UART, and then you can do that and hook it up with a 7-segment LED. So I give you the complete command, and you should be able to reproduce this work and make sense of this from here. Right? I mean, the part about TMOD, TH1, SCON, TR1, that's just treated as magic for now. That's initializing serial port. If you really want to understand, I could explain, but it's not really relevant to this course. The data sheet gives you all the details on this. But anyway, so that's really part of setting up the UART. Okay, so this one will take UART and then display into your 7-segment LED. But you better type something that is between 0 and 9. Don't type an A. Don't type something else. It's going to overflow. Okay, and then there's the interrupt version. So how do you do the interrupt version? So there's a special syntax for it you have to pay attention to, which is, you can call it any name you want. I mean, I just call it serial ISR. It doesn't care about the name. What it cares about is this special little clause after your function. So after the parameter list, double underscore interrupt 4. Interrupt 4 refers to the UART ISR. That's what matters. So this is not treated as a regular subroutine. This is treated as an ISR. Why? Because a regular function or subroutine returns with RET. An interrupt service returns with RETI. Okay, that's what tells the compiler how it does it. Okay, so that's the difference. So different ISRs will have a different number. That's how it tells them apart, and then it knows to locate them properly in the place. Okay, and of course the syntax is going to be different. But in the end, the linker will figure out, and hex file takes care of it. And then here, I mentioned another way. So you could do call to main, or you could do this. And then, oh, what does this do? Oh, here, right, another thing. Your stack pointer on power up, stack pointer is a 7. And then in 8051, you could actually move the stack pointer elsewhere. Why? Because you may want to use the register file differently. Okay, so if you want to use anything from address 8 and other than for stack, then you want to move it somewhere else. So we'll just do it for 57 for now. Later, when you do threads, you actually have to explicitly move the stack. Every time you switch the thread, you move the stack pointer to the space for that particular stack. You could do it with a move, or you could do assignment SP gets hex 57. That's fine too. Okay. Anyway, so try this out, and you'll see. I mean, you could type in the character displays on the 7-segment LED. Okay. So this read ahead, and that's all I have time for. We can continue this next time.